Hello, I'm Tim and this is my talk on Excalibur. Imagine you were supposed to implement a query by hand with algorithmic choices already made, so suppose you were given a physical query plan. Even then you had many possible physical implementations of that thing. You could, for example, implement that query in a vectorized fashion or a data-centric fashion, or mixes, or with buffering, with prefetching, whatnot. And you would call those different implementations flavors, and they generate something we call the design space. And what we know already about this design space is that we have vectorized and data-centric classes of queries, and they have very different performance characteristics. On certain workloads, each outperforms the other. And they depend on the hardware. So with weird hardware, you might be able to bend or break those rules of thumb. And with increasingly heterogeneous hardware, this is likely to get worse. What we did about this in the past is we had this language called Voila, which was able to generate many of those flavors from one description. So say vectorized data-centric, SIMD, prefetching, no prefetching. However, what we try to solve here in this work is to go a bit further. We're trying to make Voila basically practical and solve the question of how can we implement a query engine that is able to exploit the design space. So typically a system is tied to one flavor, like for example vectorized, you start with that and you stick with it for the time of your system, because adding a new flavor would basically mean rewriting your engine, and then you suddenly have to maintain two flavors, which is somewhat of a maintenance hell. And also the second part is you don't even fully know which second flavor you would choose, because the design space is not really that predictable and very much depends on the hardware at hand. So in this case, we would propose to use online learning. So basically we generate a flavor and then we see how it performs, and then adaptively choose the best one during runtime. Point two, we don't fully go into this talk, is how can we explore more efficiently? What Voila used was basically random sampling, which is not the best idea, especially for our use case here, because the better exploration, the better performance will be. As one of the consequences of adaptivity, that is that exploration now is part of our query runtime. So excessive exploration will hurt performance. And the other point is a logical consequence of making adaptive choices at runtime is that you get the maximum benefit at the start of the query. If, say, you have some magic way to accelerate your query by 2x, at the beginning of the query, everything is great. The whole query runs in half the time. If you've only found it in the middle of the query, your query might run 25% faster or so. If you find it in the end of the query, you get zero benefit. So the efficiency of exploration tends to matter in those cases, and maybe we can do something better than random exploration, but more of that in the paper. So that brings us to Excalibur. Excalibur is basically our attempt to solve those questions, and is a just-in-time compiling vectorized engine. Just-in-time compiling because it generates code just in time and compiles that too, and it fits into a vectorized framework. It's based on the idea that exploring the design space is rather risky, and there's no guarantee you will find a better point than the one you already found, like for example vectorized data-centric execution. So what we now try to do is limit the downside of risky exploration, A, by using vectorized interpretation as a baseline, and then trying to improve upon that. And B, because we limit exploration with a budget. So we're willing to risk, say, 20% of query runtime for the optionality of having the query run faster by a bit. Hopefully more than 20%. And a query in Excalibur runs roughly like that. You give it a query plan. It will then rip this query plan apart into a low-level plan. And here we have two pipelines of the low-level plan, they each executed after each other. First, we scan the inner relation, do some filtering, create the hash table. Then we scan the outer relation, do some filtering, and do the probe phase of the join. Here you can see the probe phase consists of 3 different low-level operators. Most of the low-level operators are so-called white box operators, because we can look inside them and they're implemented in voila, which has the nice advantage that we could actually optimize across them too, which we do, you will see at a later point. And then we run each pipeline, which means first we generate code, execute that generated code for a little bit. If we're not done and have enough budget, we're willing to choose a new point in the design space, a new flavor, and generate code for that, execute it for a while. If you're not done and don't have enough budget, we just stick to the best flavor we found so far. And if at some point we will be done with the pipeline, then we go to the next pipeline or produce the result of the query. You might notice that we very often generate code. And you might also argue that this is very expensive because it might trigger a compilation pass. We have some precautions against that. So for example, we use a code cache to cache often used fragments. So basically for them, we have 0 compilation cost. And we generate code in 4 steps, which are rather generic and gives us many possibilities. So step 1 is we apply high-level rules on the low-level plan level. And this, which means, for example, introduce a new operator, reorder operators, etc., or tag operators. And step 2 is we select which voila statements become code fragments. So basically, it's some assignment problem we're trying to solve there. So, and you can have different choices. For example, you can say, I want all the arithmetic in one code fragment, or I want all the memory lookups in a different code fragment. And step 3, we generate code for those fragments, which means calling LVM, or basically check the code cache if such a fragment already exists. At the end, we generate bytecode, which basically glues the whole thing together. And then we can start executing that code. How we generate and how we find those flavors for which we have to generate code. It's part of the exploration strategy, which you can read more about in the paper. Here, we just assume that we get a magic flavor that we want to generate code for. For example, our exploration strategy might just tell us, let's generate data-centric execution, for which we have to first inline operators into the last operator, and then say we select the whole pipeline as one fragment. Pretty easy on this high-level code generation. Or we could say, let's just introduce a Bloom filter and do not make any other changes, which means it will run a Bloom filter with vectorized execution. Or we can say, let's reorder some operators and then inline everything into the last operator and fuse the whole pipeline together, which gives us a different operator order and data-centric execution. You might argue that all this flexibility in Excalibur is actually making it rather slow, but I hope I can convince you that it's actually rather competitive in terms of performance. What you can see here is that we compare Excalibur to DuckDB, MongoDB, and Umbra. And very often it wins this performance comparison on, for example, Query 1, Query 6, and Query 9. For example, in Query 6 and Query 9, it is even faster than Umbra. In Query 6, because we can find the correct filter order adaptively at runtime, and we find out that we can solve the between predicates using SIMD, which gives us a nice boost. On Query 9, it seems that the winning combination so far is using vectorized interpretation and the Bloom filter. Also, that gives us an edge over Umbra. Staying with Query 9, if you compare to DuckDB, we'll see that we are roughly 20x faster than DuckDB and a slight bit faster than MongoDB. in query 9. If we go to query 1, we'll see that we are again an order of the magnitude faster than MonetDB and almost an order of magnitude faster than DuckDB. We now look at different execution tactics. So if you implement a static system, you have to make the choice. If you implement a vectorized system, you're usually stuck with that one flavor. If you implement a data-centric flavor, you're usually stuck with that. Those are the first two bars we compare to, but now we have the option to also have the other adaptive bars system, because we can adaptively choose between different flavors at runtime. And those three bars represent different exploration strategies, which I will just briefly describe. The first one is the heuristic, which is just exploring hard-coded points we deem to be good. The second one is just randomized. So you pick a random point and then you go with that. And then afterwards you pick a new random point, etc. And the last one, called MCTS, stands for Monte Carlo tree search, which is exploring the design space by building a tree and expanding the tree into promising branches. So the branches with the highest performance are more likely to be explored. And what you can see is, for example, if you look at query 18, you'll see that vectorized implementation performs pretty good. It outperforms data-centric, so the winning flavor would be vectorized if you had a static system. And you can see that we actually adapt to that. For example, the heuristic is pretty close to the vectorized line in terms of performance. The randomized exploration performs a bit worse because it wastes a bit more time on exploration until the budget is up, or it found a relatively good flavor. And then we have the last bar, which is MCTS, which even finds a better flavor magically. You can see a similar picture in query 9. Yeah, here again, vectorized execution is faster, but here the heuristic-based exploration outperforms because it finds the winning flavor, which is vectorized execution plus a Bloom filter. What you can see is that randomized exploration performs even worse here and eats up more of the budget. It looks like almost to the maximum of 20% query performance. And you can also see that MCTS performs pretty okay-ish. If you now look at query 1, we can see that data-centric is the winning flavor and our adaptive heuristic, that our heuristic also adapts to that. So that means we can dynamically adapt to the best flavor at runtime with some of the strategies, usually the heuristics and the MCTS strategy. And kind of makes a point for a dynamic system. If you look at it from a different point, you can have a similar plot, quite simpler in TBCH query 6, if you play with the parameters a little bit. What you see here is, again, static flavors and the adaptive here and the adaptive flavor, the adaptive choosing of flavors. And here again, the adaptive way Excalibur executes queries beats both vectorized and data-centric in terms of performance. So with this, I would like to end my presentation. What are the lessons here? I think there's no need to actually make static engine choices anymore, because you can just have those flavors in Excalibur and let the system handle it for you. If you feel the need, you can add more flavors over time and have some flexibility against future heterogeneous hardware. And also you could take advantage of it automatically without the need of creating cost models and stuff like that. And in the paper, you find some more information on how to explore the design space, how to utilize the DSL to generate different flavors, and how the adaptivity and just-in-time compile system would work. Yeah, with that, I would close my presentation. And yeah, Excalibur and Voila is both open source, so feel free to explore it, make it part of your project. Thank you very much.